All right, so are the captions working now? Fingers crossed. Sometimes they don't work until I unmute my mic, so it can be a little bit tough. Let's also get some music going here. Some, like, I did my best to find DMCA-free Christmas music, and this is what I found. So bear with me. It's like Christmas-themed, I don't need, like, synthwave kind of at times. I don't know. It's weird. Nevertheless, hopefully you enjoy the... I'm going to turn that down just a smidge. All right. Hopefully you enjoy the weird electronic Christmas music. I felt like it was getting me in the mood, so. And let's see here. No worries, Loco Padre. There will be a VOD. Love Phone's trying to get me to put these on YouTube, but it really depends on... I don't like them being there for all of posterity, so we'll see. They're not working. Okay, well, at some point we'll figure out why. I don't know what, like, the magical summoning spell I need to do to get the captions to work is, because I do the same thing every time I turn them on. I refresh them, I turn them on, and I stream. Sometimes it works, sometimes it doesn't. So, the tattoo on my chest is of the Hubble Space Telescope. I need to get it filled in eventually, but I've been lazy. And tattoos are expensive. Okay, so if you haven't heard, it's the 12 days of machine learning myths, and today we're going to be starting with linear regression. But before we even get there, I figured we should first talk about machine learning in general, because I think there are a lot of misunderstandings and misinformation and buzzwords that float around about machine learning. So I figured we could start there. And pretty much what I like to tell people is that machine learning is just, it's kind of a subfield of artificial intelligence. And no, AI, a lot of people when they think about AI think about robotics. And that's not what we're talking about. There's like AI, artificial intelligence, put into like robotics bodies or something like that you see in a lot of sci-fi TV shows. That's not what we're talking about here. We're not doing robotics. That'd be really cool, but I know nothing about robotics. Machine learning and artificial intelligence are really about trying to teach a computer to do tasks that we would think otherwise would take human intelligence. And so you might then go, okay, well, what actually is the difference between AI and machine learning? Because people seem to use them interchangeably, which is actually something I object to. So theoretically, I could write code that would be artificial intelligence because the computer would be learning some task that would normally take human intelligence. But instead of coding it to actually learn from its behavior and learn from its experiences, I would just make a butt ton of if-then statements. So I'm talking like, 7 Russian novels worth of if-then statements. Well, it still approximates human intelligence, but is it really learning? It's not. It's just checking a whole bunch of conditionals. And that's what we would call AI, but not machine learning. So the 12 days of machine learning myths, we're going to be talking about how do we teach computers to learn things, and what does that even mean? And we're going to start off with things that are very, very, very easy and simple, and you might even sit there and be like, oh, this isn't machine learning, but I promise it is. But we're going to get complicated pretty fast, so it'll be good to start simple, I promise. So if you're interested, though, in, wait for it, the schedule. Which way? This is the schedule over here. This is the schedule for the 12 days of machine learning myths. You can also find more details on my Discord. So as you can see, today we're going to be talking about, is this the old or the new schedule? Oh, good. I did update it. Yes, this is the updated schedule. Mainly because I have the next 2 weeks off from work and I'd really like to enjoy some of it. So I figured I'm gonna squeeze in a couple of days off, plus there's some fire station training and other stuff in there. So we'll be going from today all the way through January 8th. And these are the topics. Oh, I know, Generic Crew. So Generic Crew is teasing me a little bit because I got my days mixed up and I thought it started yesterday. And then on all the flyers and like, you know, cool art and stuff I had commissioned, it all said December 19th. So I got the 19th and the 18th confused. But it is the 19th today. And we're going to be getting started. But so if there is a topic you're really interested in, stay tuned. I will say that some of these do build off of each other. So if, for instance, you're really interested in reinforcement learning, it'd be really good to come to both the reinforcement learning, the neural nets 101, and the Q networks sessions. But also, I mean, I find it all interesting, so I think you should be here for all of it. I'm just saying. All right. So with that, let's get started. So, okie doke. Your ML brain was ready yesterday? No, Onad. Stick around, please. All right. I know, isn't it cool, like little like bow thing? I found it for free online. I was like, oh, that's really cute. And it's all holiday themed, so I figured that would be... Finally, I get to put all my like kitschy effects and stuff that are super like probably 15 years old, but whatever. I think it looks awesome, and if there's a time to be kitschy, it's the holidays. So, alrighty. So, like I said, we're going to be talking about linear regression today. And that kind of begs the question a little bit, what even is regression? And so regression is a type of statistical analysis where really what you're trying to do is either predict trends in your data or make forecasts, or you're trying to kind of extract the relationship between variables. And what this all kind of comes down to is something that a lot of you may have learned in high school, which is the equation of a line, or y equals mx plus b. And so, those of you who wonderfully, let's see if I can get this to work. I've been working on it. All right. Those of you who were super, super, super kind and donated to the stream helped me afford a little drawing tablet so you don't have to deal with my horrible, horrible trying to sketch with a mouse. So I've been trying to practice with this. Be patient with me as we go through this. I will probably get a handle on it. But look! Yay! I can draw on things. Oh, thank you so much for following Manuanda. Welcome, welcome. Okay, so like I said, today we're going to be talking about... Okay, this is the one thing that has messed me up about digital art and tablets since I was a teen is you have to look at the screen, not your hand. So normally I look at my hand when I'm writing, and now I have to look at the screen. Okay, all right, I'm good. I'm going to get used to this, I promise. So today we're going to be talking about linear regression. Yay, and if you can't read my terrible handwriting, I'm sorry. It's been horrible my whole life. I can't do anything about it. Etch-a-sketch. Yes, I want an etch-a-sketch. Okay, so like I said, where we're going to start is y equals mx plus b. Do people remember this? If you don't, speak now or forever hold your peace. I have no problem doing a little like review, but if people don't remember, it's gonna get wackier from here. Okay. So, okay, you don't. No worries. All right. So, this is... We're gonna give ourselves some cool effects here. This is an equation of a line. Line. This is gonna make your brain think linear. Ah, yeah. And so I like to make this connection now because a lot of times people are like, oh, linear regression, the math is going to be really complicated. My friends, sit down. We're just talking about lines today. That's all we're dealing with is lines. So let's go back to our happy Cartesian memories here. The thing that makes us all so happy, right? Oh, yes. Look at this beautiful, beautiful. I'm just so excited that I don't have to write terribly anymore. All right, and let's say that we have, oh, car what now? Oh, wait, is this like space? Galaxy pen? Hold on, excuse me one moment. Okay, I'm good. I'm focused. I promise. I told myself I'd be way more focused than normal for you. Okay, we have to draw the line with the galaxy pen now. Oh, okay. Focus. We're good. All right. Makes you certainly happier than polar. Oh, I've been working on a work project now that is all like Fourier transforms done in log magnitude and log polar space, and it's just so beautiful to simply see X and Y. It's really nice. I did geek out so hard I was speechless. And hi Sam Fair, welcome. Okay, so let's start with the equation of a line. All right, so actually, all right, and yes, the line is going to be galaxies. All right. So, okay, well, let's just pretend that goes through the 1. All right, now the equation of this line is, let's see, we've got a point here. We've got a point that's at 0, 1. Also, please be patient with me. I've been dealing with images a lot, and the X and Y, the convention of having X comma Y for your coordinates is switched in images. So I'm going to try my best to, all right, and then we have 1, 2, right? Okay. So these are just points on our line, right? And a line just being a whole bunch of points all connected. Let's see. Loaf gets that way about loaves. What? And oh, hi Nexus, welcome. We're always throwing away bread. I feel bad, but Loaf buys way too much bread. All right. So when we're looking at this y, I'm going to write it a little bigger so we can kind of see what's going on here. Y equals mx plus b. This is an equation for a line. So it's just, when you think of equation, you can kind of think of like a pattern, right? Equation, function, same thing. In this case, our function is just relating 2 variables here. So we only have 2 variables. We're going to make them galactic because obviously we've got our y and we've got our x. Then the m and the b here are just numbers, okay? They're just constants. And you might be asking, what's the m, what's the b? So in this particular case, the b represents the y-intercept. You've probably heard this. This is literally just, where does it hit the y-axis? So in this case, we actually already know this, right? So we can say, oh, we actually already know our b. We know it intersects with the y-axis at 1. And the m, no, I was using blue. I'm getting way too excited with all these colors, is the slope. And the slope is just how steep the line is. In this case, we're going, let's see, we're kind of going up 1 over 1, up 1 over 1. So our slope here is just 1. So we can even just, we'll put a 1 for the sake of having it here, but we wouldn't even need to write it. And what this equation is actually telling us, though, is it's telling us how is x related to y? If I had y, how do I get x? If I have x, how do I get y? How are these 2 variables related? And when we write it like this, what we're really saying is x changes and affects the y, right? If we were to change x, if I were to plug 4 into here, our y would change. So that's why we often refer to these as independent and dependent variables. And so y is our independent, no, y is dependent. Oh, shoot. I'm used to just writing these actually as, no, y is independent. Independent variable, and x is dependent. Do I have those? I always swap them. Do I have them swapped? Someone tell me if I have them swapped. They always look wrong. Anyway, regardless, one depends on the other. I feel like I've swapped them. No, y just feels, they are swapped. Yes, okay, thank you. This is one of those things for me. I always switch the names here. Independent. Ha! Well, you know what? That's why the eraser was invented, right? So nobody can tell when we make mistakes. All right, so that's because when we change the x, the y changes. The y is dependent on the x. This is a really easy example though, right? Because we've got like one x value corresponding to one y value, right? And so we could have a whole bunch of x's. We could have like 0, 1, 2, 3, etc. as our x values. And they would correspond to a bunch of y's. So we plug 0 in, we'd get 1, 1 in, we'd get 2, 2 in, we'd get 3, 3 in, you'd get 4, etc. as our y values. Oh, look, it's all Christmas. And so you can have multiple values easily representing your x and y. And this is what I think a lot of people get tripped up on. Oh, thank you so much for following Tixel Geek. Welcome. I almost said Tinsel Geek. I'm just like really feeling the holidays today. What we're gonna do with this is instead of talking about a single x or even a single set of x values, we're gonna say, what happens when we have, our y, which is really what we're interested in, and then we've got a whole bunch of different x's. So maybe we've got an x that represents, let's talk about the weather, right? So we really want to predict the weather tomorrow. And maybe we've got an x that is our temperature. Maybe we've got an x that is humidity. I don't know weather very well. We've got an x that is barometric pressure. I think that also affects the weather, right? Yeah, there you go. Whatever. Anyway, so you can have a whole bunch of x's. Here's a spoiler alert. These are going to be called our features. So when you talk about machine learning features, you're talking about your x's. You're talking about your independent variables. You're talking about the things that you plug in to your equation to get your answer. Our y here is our label. This is the thing you also hear called like your target. It's the thing that you want to predict. You never liked your x's. Well, in this case we do. We like our variable x's. And so all of this is actually going to turn into, let's see, clear canvas. All right. So now that we're, okay, we've got our little bit of a refresh of our equation of a line. I'll put it up here so we can remember it. This is our simple line. This is our high school line. But we're talking about machine learning now. So we want to really, crank it up a notch. All right. So what we're going to be working with is going to look really, really similar. So don't panic. We're going to have some more letters in here, but don't panic. We're going to go through them all. All right. So don't run away. All right. This should look, it's similar. I promise. Really, this is just all of these m's. If we have a whole bunch of different m's, we just need all of those different m's to match all of the different x's we have. And because we're fancy and we want to feel smarter, we're suddenly going to use beta instead of m, but really we could seriously just write this. Oh, we're using m. And then e. What is this crazy magic? And hepta. Hold on, let me see. I'll catch up on chat for a second. I'm trying to balance chat a little better than I normally do and not get too distracted. So, would you relocate to the other side of the country? I've lived in California plenty, and I love I love California. I am actually trying to leave the United States. So if it was a really amazing job, I would totally move wherever. What happened to the good equation? No, it's still here. Our good equation is still here. It's not going anywhere. This is where we started. This is our true love. We are just writing it out a little bit more, okay? Because remember how earlier what we were saying is, all right, we've had one x, and that's cool. But like, what if we have multiples? So what if we're trying to predict the weather? If we only use temperature, that's not going to be enough. We need to use temperature. We need to use humidity, maybe even yesterday's weather. So we need a lot more variables to base our prediction off of. If we kind of cut ourselves short and we limit ourselves to only one independent variable, we're not going to have all of the data that we really need to be able to make an accurate prediction. So if we want to predict y, and we have a whole bunch of different x values to use, a whole bunch of different kinds of x's, well, we want to use them. And that's all this is doing. This is expanding our equation, and it's saying, well, what happens if instead of just a single x, we have a whole bunch of different x's? So this here, This is kind of like just your intercept, right? Because think about it like this. This is where x equals, this is when x is 0. What is y equal, right? So when x is 0, we just have this m. Here we called it b, but here, just to keep that nice naming and not my terrible handwriting. And all the way down, this should all look familiar until we get to this weird thing. Don't worry too much about this just yet. This is going to be our error term. Too many x's need to settle down. And then here for chess vids, you say, when I am working with machine learning framework, if I can't answer what you do now, how about another pointing career? How many independent variables do you tend to work with? Let me define a term first. Oh no, you can't see it. Okay. Oh, poop on a nugget. All right. Hold on, friends. Let me make a little, I'm gonna make a little line for myself up here so I know where the cool little effect thing that I made is. All right, so I made myself a little line. That won't happen again. So mn(xn) plus eta. All right. It's so cute, I know. I moved it. It's right here. This is our error term. I'm so sorry. I just got that thing. Isn't it cute? It has snow, and it just made me really happy. So, all right. But to answer your question here for chess vids, I need to first define a term so that you know what I'm talking about. When we are dealing with, let's say this is our equation right here. Our little happy equation, right? If we were to look at all of those independent variables, right, that you're just talking about, all right, so we've got this just means vector, all right? Now we're going to deal with x1, x2, all of these things, all of our independent variables. Maybe if I write it enough, I'll remember. This is what we call in machine learning, this is our feature vector, all right? That literally just means all your x's, all your independent variables, all the inputs. Also, you can think about these as your inputs. So you were asking me how many independent variables do I deal with? Another way to think about that question is how large are your feature vectors? And I've dealt with a lot. I mean, and it really varies based on the project. It is not unusual to have them be thousands, if not tens of thousands of variables. And that's really where you start to working with linear regression. I want this to be as explainable and I want us to visualize it a lot and for it to kind of feel intuitive by the time we're done with it. But once you're dealing with feature vectors that are that sized, it's really, really hard to picture it in your mind. It is. It's like you can't quite visualize. You just can't visualize it anymore. But no matter how scary, no matter how many variables that feels like, just come back to what we were talking about earlier, which is our line, okay? This is all we're doing today. The only new thing that we're really going to add, can I make these different sized? Wait. Oh, yes. Is we're going to have a bunch of data points. Here's all of our data points. Yay. Data. We love data in this stream. Kind of looks sort of pretty. Kind of looks galaxy-like. All right. And we're going to be trying to fit a line to that. That's literally, was this the thickness I was using before? Good enough. All right. That's all we're doing. It doesn't matter if these wonderful little data dots are in 1,000 dimensions or if they're in 2. It matters a little bit for the computation, but for your own purposes, when you're conceptualizing what is linear regression, linear, line, you're fitting a line to it. That's literally all we're doing, okay? We're going to take some data and we're going to fit a line to it. And for that, am I still using the Galaxy pen? I gotta use the Galaxy pen. All right. And so for that, we're gonna need a couple of things. When we talk about machine learning, one of the things that is really, really important is, you'll hear this term coming up a lot, your loss function, okay? All this really is, it's a measurement, it's a function that describes you are. That's literally it. It's like, how bad is my model? Let's make a function. Oh, Frecht Chemist. What a wonderful name. Thank you so much for joining us. How obscenely big might an actual one be? An actual what? An actual feature vector? That's absolutely, yeah. 1,000 dimensions. I mean, think about it like this. A lot of times when you're dealing with like computer vision and trying to, this isn't fully, it doesn't map exactly, but like a lot of times you might be feeding in pixel values. Actually, yeah, no, that fits because I did that with an astronomy project where we were feeding, so our inputs, our feature vector was all of the pixel color values for galaxies. And some of our images were 100 by 100 pixels, 500 by 500 pixels. Suddenly that's a lot of inputs that you're having to feed into your machine learning model. So we will talk about dimensionality reduction. We'll talk about PCA, not on this, not today. Today is just, we're just getting started. We're warming up. This is linear regression only. So when we're thinking about, just making sure I'm staying on track as well. I wrote notes. You should be so proud of me. I wrote a bunch of notes so I would stay on topic. The reason why we have a loss function is this is what we tell our program to minimize. So we're not just like, if we go back to that idea of, yes. Okay, let's actually use maybe a color that's a little easier to see this time. If we have all of our data, look at our beautiful data, and we want to fit a line to it. Well, how do we fit a line? Where do you start, right? Each of these points here is an XY value, right? And then we have a line that's trying to predict where they're going to be. So how do we say that this line is a better fit than this line? Well, obviously by looking at it, but how do we define that in terms of math? Well, in this case, what we're going to do is we're going to use kind of a standard error function, a standard loss function for linear regression, which is called sum of squared errors. Can you see that? Yeah, okay, good. And this leads to kind of, you might hear ordinary, least, squares, regression. These mean the same thing. It's just saying which loss function we're using. And in this case, and don't panic, we're gonna have math for a second. Okay, we'll talk about we'll talk about that much later, generic crew, but not for like, machine learning 101 linear regression. We're not gonna jump into that just yet. All right, actually Adam W is better than Adam, just saying. But what was I? Ordinary least squares regression. So don't panic at first. We're going to break down what this math means. Okay, so I'm going to write something that's math. Don't run away. We're going to break it down. So okay, I know there's math, but don't panic. All this really is we're going to sum. Actually, let me change. Sum our squared errors. It's literally all it says, folks. We're summing our errors that are squared. And here R is our error. So then the natural follow-up question might be, well, then what's R? How do we define that? In this case, we're going to say it's our the actual, so the y that's our true, our y, our actual y, minus the y that we predicted. So it's the distance between these two. So you can think about it like we're taking the distance here between each of these points and the line, and we're saying how far were we off on average? And there are other error loss functions and error metrics that you can use, but this is the one that we're going to be using today. This is not R sub 2, this is an I. Sorry, I drew over it a little bit with my arrow. Yes, this is I. No, it really the green arrow really wants to be on over the I. But yes, that's an I. So for each of our predictions, I through n, we're going to square them, and then we're going to add them all up. All right. And so one of the cool things, the last thing I want to mention before we get to coding is clear canvas. Is why we're interested in linear regression and some of the assumptions we might be making. So linear regression, in case new people come by and they're like, the hell is all of this? All right. Okay. Why use linear regression, or like what some of the assumptions that we're making here? Oh, super fly. Thank you so much for following. Hi David Ames, welcome. So assumptions that we're making here. Well, here's the most obvious one. It's in the name. We're assuming that there's a linear relationship between X and Y. We're assuming that it is a line. If we had like and we tried to fit a line to this, like, we're gonna have a little bit of a bad time. It's not gonna be, oh, there's other colors. Okay, nope, leave it. You know, maybe this would be a better fit for, oh, I don't know, say a quadratic. Maybe. The difficulty here, or the assumption, the main assumption that we're making is that there's gonna be a linear relationship between X and Y. And yes, V. Galvez, it's also a good starting place for that reason as well. And David Ames, you say you have a question? Yeah, hit me with your questions whenever. I'm trying to balance looking at chat because I can also get really distracted just hanging out with you all and talking to you. So if I don't see it, hit up Loafbone and he will highlight it for you if you don't have the channel points. He tries to ensure that I don't miss too many of the questions. Okay. But one of the really interesting things that I like about linear regression, and honestly, lots of machine learning algorithms can do this, but this one's really explainable. I feel like it's a lot more intuitive to understand this idea of having a scattered bunch of data and trying to map a line to it. There's something that feels kind of Loafbone. David Ames, you say, when there's a solar flare, how do we know in advance if the particles are traveling at the speed of light? Well, space being a vacuum, anything that is light-based will travel mostly at the speed of light, unless it's like attenuated through dust or something like that. Why specifically are you talking about solar flares? I will caveat this with I'm not a heliophysicist, and I checked my stellar astrophysics boxes in graduate school, but I didn't study stars. So I'll put that gentle caveat. Like, usually in a lot of astronomy departments, there's like your normal astronomy that's like galaxies and exoplanets and stars that aren't our sun. And then there's like a heliophysics department that always was somewhere else. I'm not sure why they like weren't part of the astrophysics club, but sometimes it's computer models, David Ames. Sometimes it's we don't necessarily get advanced warnings. Some of the particles, some of the like charged particles and stuff, how to put this? We have the Solar Dynamics Observatory that orbits the sun. And so we're able to take really advanced and really detailed measurements. And sometimes that'll help us kind of predict. I believe, if I am remembering correctly, there is a kind of like early warning system that happens when the solar flare starts, and then the solar flare itself takes some time. And then our satellite relays that warning back to Earth, but obviously it's not a lot of time because I think it's like 8 minutes, roughly 7-8 minutes that it takes. for light to travel from the sun to Earth. But if some of like the radiative particles happen kind of a little bit later in the peak or something, we can have a couple minutes of warning. But honestly, it is not very great. And especially for very, very massive, like, coronal mass ejections and everything, that's something that we really want to work on, is how do we predict these better? Because if there is something that, say, knocks out a power grid, that is really a threat to life and a threat to safety on Earth. So it's something we need to get better at predicting. Yeah, super cool question. And hi, user 129835. I know, I'm trying to be good about not cursing because I tagged education in the stream title. So I've got my, like, teaching hat on, and I usually try to not swear when I'm teaching. Okay, but really quick, back to linear regression. That equation that we were looking at earlier, so our kind of like y equals, can you see the purple? Okay, yeah, all right. So y equals, I'm going to use m still, so our like mx plus b, also because it's easier to write than beta. But also to kind of, I want you to always be thinking about that y equals mx plus b equation, all the way to mn xn plus here. All right. So in this case, if you look at the coefficients, so you're looking at the constants attached, usually to a variable in here. In this case, our variable isn't there. But if you look at all of these constants, right? So we can say, maybe just like we did with the x's, right? We can group all of these together. Oh, thank you for following user 129835. If we group all of these together, you'll hear these go by a lot of different names in machine learning. You might hear, like, you heard me just say coefficients. Snoots! Okay, hold on. I will pull up the snoots in just a second. Let me get through this thought or I'll totally get distracted. And it'll be a good stopping place anyway. You also hear them called our weights. And so if you're hearing about, oh, like, you know, it's literally okay, it's literally weight training. When you hear about like you hear people say about training a machine learning model, what we're saying is we're trying to figure out these m's. We're trying to figure out the coefficients. We're figuring out the weights. That's what training is. It's all about the weights. And in this particular case, one of the other great things about linear regression is that it maps directly to the importance of each of these features. So if I have, you know, if I fit my line to my data and I get, you know, an equation that's like, they're going to be a lot more complicated than this, but just bear with me. If we have something like this, what this is telling me is that when it comes to predicting y, the value of x2, whatever this feature is, maybe this is our weather, all right? And this is temperature, and this is humidity. I really don't know. We're just making this up. And what this would actually tell us, if we're trying to explain our model, explainability is really important in machine learning. If we're trying to explain our model to someone, it's very easy to extract from this what the importance of different features is. So here, this is saying, when it comes to predicting the weather, humidity is hugely important. Its weight is so much higher than temperature. Obviously, I don't even know if that's actually real. This is just an example. But that's one of the other benefits of linear regression is as your model becomes more complex, you're losing out on explainability. You're losing out on the ability to sometimes easily tell things like feature importance. It isn't always true, but there is a trade-off when it comes to complexity in models. The complex ones are really fun. Like, don't get me wrong. I love building really deep neural nets and stuff. But honestly, the models that I come back to the most when it comes to supervised machine learning are regression, because a lot of times it gives you a great place to start. It gives you explainability. There's easy ways to visualize results. There's easy ways to tune them and to make them perform even better. And also, it's very easy to extract some of these key results. All right, so we are going to be using Python today. This is just a blackboard. This is not Python. We will be getting there though. Okay, so hold on, please, while I set up, because someone, Onad, I believe, wants to support the snoots. And so let's pull up our Furbo camera, and let's give some treats. Let's give some treats to the boys. All right. Oh, I think you see a Hubble there. Let's see. Hubble, here's a treat from Onad. Let's see. I think he's sleeping. Oh, he's not sleeping anymore. Wake up, Hubble. Get your treats. Oh, the world's slowest getting up. What a little nerd. Oh, good boy. We'll give you 2 treats because you're just such a good boy. That got his attention. Yay! There you go. Thank you so much, Onad, for giving some wonderful treats to Hubble. Tennessee's probably under a blanket or he would join in. What a good boy. All right, well, I am finding where I stashed our notebook for today. We can just look at how cute my dog is. There it is. All right. So for this, we're going to be using a Jupyter notebook, but and I'll explain why. But for future sessions, the more complicated models, we won't be able to do them in a Jupyter notebook. But for this we will. He's so cute. Oh, and he's getting water like a really good boy. Okay, I have to tear myself away, or I'll never leave my dog. So cute. Hubble does hydrate. Hubble's a very good boy. Okay, I have to stop looking at him. All right. I love my dog so much. All right. So we're going to be using something called a Jupyter notebook. This is a handy way to do some code in a way that's really responsive, and it's kind of cool because we can run it line by line or cell by cell, and we can also stick in Markdown if I want to show you some math, and also we'll be able to see our visualizations right in line. So we're gonna start out with just importing some libraries that we're gonna use. So give me 1 second. Play among yourselves, class. Or if you have questions, let me know. And then I'm just gonna copy these ones because there's a style I like for Matplotlib. Oh, thank you so much for following Datakiss. Put the data sets up for you to download. We're gonna be using the Boston dataset today, the Boston housing dataset. And thank you for following Toel. This is one of the things I wanted to accomplish with these streams is not just teaching you, here's some language to talk about machine learning, here's how some machine learning is done, but also to introduce you to some of the most famous data sets, because these are ones that you might see in a technical interview. These are ones that a lot of people will talk about. And also, because I promised you we wouldn't do too much EDA because we've had so many streams on that, a lot of these are pre-cleaned, so we won't have to do a lot of the cleaning. But yes, a hacker, the Boston housing data set. So you can, if you have scikit-learn installed, you can just do this. And do I need to set I don't know, it's boston.data if I remember right. And then we have our data. Size up the font a bit. Oh, Lord. If I remember right, these are a pain in the butt Jupyter Notebooks can be a pain to change. I had to do a whole bunch of stuff last time to change the, let me see if I can do one thing. Give me 1 sec. I will try this. I tried this before stream started and it didn't work. But if you give me 1 sec here. Oh, I can just zoom in. Yeah, absolutely. Let's just do that. Duh. All right. Is that big enough? It's a little big. Is that better? Can we compromise? Is that all right? And I figured out all of the different column names and what order they were in, but I won't bore you with that. So we're just gonna set. So now if we look and we go back and we run this, we see, okay. And, oh yeah, I made a list for you all. Hold on. Where did I put the list? Here's the list. So, oh, this is Markdown. Ah, stop it. Markdown. All right. Your old man eyes. So is that better? Your old man eyes can see this. All right, so we're gonna be dealing. Give me one sec too. I need to add in. Oh no, it's Boston.target. Okay. So this is a Jupyter notebook. It's not a Google notebook. But this is pretty fast. I would say if you're going to be dealing with massive data sets though, like you just don't use a Jupyter notebook. Jupyter notebooks are good for smaller data sets, for visualizations, and for starting out and for taking notes. So I wouldn't recommend them for some of the heftier machine learning models. And once we get into those models, we're not going to be using Jupyter notebooks anymore. But I find that there's an intuitive nature about Jupyter notebooks that is really good for teaching. So I like to use them to show people new things. Okay, so what would I use for the bigger data sets? An IDE. Just like instead of running your code in a notebook, just build your models in your IDE of choice. I mean, ideally it'd be great if we all had like billions of GPUs on some wonderful server that we could just write our code on and like do it that way, but most of us don't have that. So in any case, this particular data set is really, really good for trying to predict this at MED-V. It's the median value of owner-occupied homes. And so we can even look at that. So now, there you go. This is kind of what it looks like. And we have all of these other features, right? So this is going to be our Y, right? This is our dependent variable. And then we have a whole bunch of independent variables, a whole bunch of X's, right, that we can, that we're going to be using. And so you can see things like crime, like the per capita crime rate in the town, the nitrous oxide concentrations, accessibility to radial highways, okay, proportion of owner-occupied units built prior to 1940. This is not the most interesting data set, but it is really good for learning because it's clean. Means all of the null values have been replaced or kind of cleaned out. And all of our features are numbers, which is really, really good. We need floats, we need integers. We do not need categorical variables. If we have categorical variables like color of the house, we would have to do something about that. And so all of that ugly stuff of figuring out, what do we do to our null values? What do we do with our categorical variables? What do we clean out? How do we normalize this? Most of that stuff happens in the data processing, which we have done streams on. So I wanted to skip past a lot of that, not bore you too much because you're probably like masters at it now because we've done enough streams on it. So we'll be dealing with a mostly cleaned data set. Is the cry per capita on top because this is America? Oh, goodness. Yes, and so, but here, V. Galvez. Yes, if we had NANs in our data set, we could use the fill NA method that is given to us in the data frame class from pandas. However, it's actually a very interesting methodological question of, do you drop them? Do you fill them? And if you fill them, what do you fill them with? And it's not as easy as you think. Like, when I was first starting out, I thought, yeah, just fill with 0. It's fine, right? Well, not if every other value is like in the hundreds or something. If you're just filling your nans with zeros, that's really, really kind of offsetting things. So there's different rationales and cases where you might want to fill with the mean, you might want to fill with the median. Those are all possibilities. If you have a massive enough data set and it won't really hurt your class balance, you can just drop them. There are lots of things that you can do. And I just give some spice to the model. Oh God. If you mean by spice, you mean like makes data scientists cry, then yeah, probably. All right. So one of the lovely things that Pandas does give us is there a space there? That shouldn't be there. Enough of that. Is that we can do data.describe. And this gives us some wonderful basic statistics all about our beautiful, beautiful variables. One of the first things that I look at is the count. And we're good because it's pre-cleaned. Oh, if these are different, sometimes that means that you have nans. And so you can also try to count and say, are we sure? Are there any nans? And oh, look at this beauty. It's pre-cleaned. If only all data came like this. Wouldn't that be really, really nice? All right, the other thing that we should probably take a look at, right, is the distribution of our predictive variable. So it's Gaussian with a tail. So not the worst, trust me. And for this purpose, this will be fine. If you have data that is heavily skewed, or your label, so the thing that you're trying to predict is really skewed, or it has like a really weird distribution, you can run into some issues. So it's always good. We're not going to mess with this plot too much. Honestly, I'm sorry. I love you all. I don't like data visualization. I like when other people do it. I don't like doing it. So we're not going to mess too much with it. This is a sanity check to go, how does our variable look? Yeah, it looks cool. All right, good enough. Okay, and so I'm gonna import some stuff that we're gonna use. So just give me 1 second. I hate doing this. I hate having to put the imports because it's like I'm giving away spoilers. You all are gonna see what I'm gonna be talking about. It's like, no, I wish I could hide them so you can't ever see them. You seem good at this. You ought to consider doing this for a living. You are teasing me, right? Well, I do a fair amount of linear regression, I have to say. If you had asked me a year ago, the clients I was working with and their data, I was doing a lot more regression. Nowadays, it's really complicated. Like, I posted this snap of the math that I was going through for some software I'm building, and it was like, the amount of crying emojis I got back from people being like, what the actual hell is that? I was like, I love it. It's awesome. Thank you, Eric OF23, for following. What train does shush, generic crew? We're not going to go too much into that because that's something else we have also talked about. And thank you for following Quem Exordium. Mark Zuckerberg loves balls. What an interesting name. PyTorch, TensorFlow, or other. So for this, we're just using scikit-learn because it's just basic linear regression. Later on, when we're getting into our more complicated models, I like a combination of Keras and TensorFlow. Me and PyTorch don't get along. I don't know. I broke up with PyTorch. Like it's not the best relationship anymore. So we're not going to be using PyTorch unless I have to. All right. So a couple things. Let's start out with the most basic, right? Because I think one of the best ways to learn is to show you what happens when we just try to fit a line to it. We're not going to do anything fancy. Let's see what the hell happens, right? Okay. So we know our y. What is our y? It's that median home value, right? And what is our x? Our x is everything else for now. So we're going to do this data.drop. That just means screw this particular column. Now we have our x's and our y's. Easy, right? So big companies are moving towards PyTorch and abandoning TensorFlow. Not the big companies that I've seen. And I can tell you this, NVIDIA, who I'm usually following their lead with a lot of stuff, at least the last time I worked with them, which wasn't too long ago, still are all about the TensorFlow, and for good reason. I mean, a lot of times, though, it is splitting hairs. Like, all of these libraries are good. If you love PyTorch, go for it. I just had better luck with Keras myself. But I did PyTorch for years, so that's not... And Snakebite39, thank you for following. All right, so this is really, really basic, right? We know our y. Just think back, y equals mx plus b, right? All we're trying to do, we got to figure out that m, we got to figure out that b. We know our y's, we know our x's. Everything else could be, still? Okay, hold on. 150%. I'm going to start giving myself a headache. All right. Is that better? Can you see that better? And thank you for following Angdalon. Angdalon. I keep wanting to say Anglodon as if it's like some kind of dinosaur. And me too, if I missed you. Thank you for following. And Snakebite. You are a Python noob. No worries. Python noobs are welcome. All noobs are welcome. We're all noobs in something, so it's fine. All right. First thing we got to do is we need to split our data. Because here's the problem. Is if I train, right? Remember what training means in this case. We're just figuring out those coefficients. We just want to know those m's, right? But if we train on the whole data set, we're going to run into a problem that's called overfitting, which is that our data or our model might learn really, really well how to predict this median value for the data that it's given. And how will we know how it's going to perform on data that it hasn't seen yet? Well, we don't. So we have to do something called test train split. Thank you for following Endpoint. And yeah, Loafbone is trying to strong arm me into putting it on YouTube after. I didn't commit because if I made a fool out of myself, I was going to say no. But if people enjoy it and there's going to be some benefit from it, then absolutely, let's put it on YouTube. Is it better to have a giant monitor, a giant font, life or death situation? I have 3 monitors. I can't tell you, as my stream has gotten more complicated, the amount of windows I have right now is just... And Mark Zuckerberg loves balls. I love answering your questions, if only to say your username. I am not a researcher, like an academic researcher. I work in industry. I'm a machine learning developer, but it involves a lot of research. So I research lots of things, but I would not say I'm not an academic researcher. Okay, so like I said, right? We can't have overfitting. We need a genuine way to test how good our model is. So we're going to do something called test train split. It's exactly what it sounds like. We are going to split our data and we're going to hold just a little bit back. We're going to keep it away from our model. We're not going to let our model see it so we have something genuine to test on. Now, big caveat here, which is that when you're dealing, let's say we're doing a computer vision model. And that is literally, I think, the last day of stream. But still, let's just say we're building a computer vision model. We want our model to be able to tell us, to be able to identify cars in an image. Let's go with dogs in an image. Because I like dogs more than I like cars. And our data set, we test train split because we're good machine learning developers, right? But our data set is all full of dogs in urban backgrounds. And suddenly we show it dogs that are in the wild or dogs that are swimming or dogs that are in a snowy area. Well, our model might do way less well on those images because they're very different from our data set. So I want to put that kind of caveat in here that test train split is by no means somehow like this wonderful, perfect way of being like, yes, my model's actually performing, because you're still, the bit that you're holding back is still from the data that you're using. Thank you for following Khaki Wacky. I love your names. Hydrate. Cheers, Loafbone. Okay. Actually, let's take a tiny, tiny break for a little machine learning story for you all. Like, circle around, my friends. Because I found this hysterical. There was a machine learning computer vision algorithm to predict whether or not the animal pictured was a dog or a wolf. I love this so much. This is why test train split isn't perfect, also why your data really matters. And I've been so good at not swearing, but this is a good case where I'm gonna swear. Everything in machine learning follows one sacred principle, which is shit in, shit out. Doesn't matter how beautiful your model is. You give it crappy data, you're gonna get crappy results. So in this particular case, wonderful, wonderful, intelligent, brilliant machine learning people, oh wow, like, great model. Can tell a dog from a wolf in a variety of different situations. So great, until they realized that what the model had actually fit to was whether or not there was snow in the image. Because all of the images, or most of the images of wolves that they had given the model to train on, were in snowy conditions. So the model actually didn't learn the difference between a dog and a wolf. It learned to identify whether or not there was snow in the image, which I thought was hysterical. So again, machine learning's complicated. The results you get might not always be the results you think. All right, Onad, I see your no cursing for 5 minutes. I can curse again. Not that I have been very much at 8:12. So, hi, Nairo. Yes, you did join at the best possible time. We're going to be having 12 whole days of machine learning miss. Please swing by the Discord for details about the schedule, or if anyone has more questions after the stream, because I'm going to be doing 12 of these streams and I'm really trying to also have some days off. I'm going to be limiting how long I'm going to stream, so I'm only doing about 2 to 3 hour streams, so that I can keep my stamina up. But if you have more questions, I love talking about machine learning, so join the Discord. My dog loves snow. Also a perk of being in my Discord, you can see pictures of my dogs. Okay, so let's see. Thank you for following. Mark Zuckerberg loves balls. I hope you keep talking in chat because I really love your name. And yes, you were right. It was a snow detector. Just hysterical. All right, so let's get back to this. Let's split our data into our testing sample and our training sample. And actually here I haven't normalized it, so oh, Bernese Mountain Dog, yes, please. Hi, Shy Ryan. I want a Bernese Mountain Dog. The only thing that makes me sad is, like, I love giant dogs, but the more gianter the dog, like, the shorter their lifespan, and that just breaks my heart. But Bernese Mountain Dogs are one of my favorites. They're so cute. All right, focus. All right, so it looks like I picked. And we're not going to go into, at least not in this stream, not yet. We're not going to go into the test size. So we're saying we're going to hold 30% of our data back. And there's logic behind how much you hold back. We're not going into it yet. So stay, a family of 5 Bernese. Seriously, if you like dogs, go Google Bernese Mountain Dog and your day will be better. I promise. Did I spell it wrong? Did I swap it again? I always do this. I have written these words so many times and I still swap them. All right. And let's instantiate our linear regression. And then we're going to fit it. We're going to fit it to our training data only. And let's see, what does it look like? Capitalized it. Not bad. Not bad. And also, to be fair, so before anyone's like, wow, this is amazing right off the bat. Yes, it is. But this is a heavily cleaned, heavily normalized, like well-balanced data set that is used for out of the box ONAD. Like higher is greater, absolutely. But out of the box, that's not bad, honestly. I've had far, far worse. Just no, we haven't done anything with hyperparameters. We haven't done anything with our data. We've literally just fed it right out of the like Excel or whatever it is, CSV. And that's what we get. That's not bad, to be honest. And Nairo say that your completely uneducated viewer who has 0.01% knowledge about programming, so I'll just watch you. No worries. Though seriously, if you have questions, please speak up. I'm sad that you missed the earlier part of the stream, which is where we were going through the concepts, because we did start out I really want to keep these as accessible as possible, but each day will build off previous days. So hopefully you'll be able to catch the VOD and kind of learn at least some of the concepts. Don't worry so much about the programming, because as we're doing each thing, I want you to be able to understand like conceptually what's going on, because you might not be a Python programmer. Maybe you want to build something in another language. And so it's more important to me that people walk away kind of understanding the concepts than remembering what scikit-learn's linear regression syntax looks like. So, and Mark Zuckerberg loves balls. You say, what is the coolest thing you've done with AI? Thank you for following, Mr. Jimbo Jones and Blowfish Fugu. Welcome. The coolest thing I've done with AI. The coolest thing I thought, or the coolest thing like the people I work for thought? The coolest thing I think I thought I've ever done had nothing to do with my job, and was me dicking around trying to build a reinforcement learning agent to play StarCraft. That was so much fun. So much fun. I loved it. I was terrible at it. My RL agent did horrifically, but it was just so much fun to learn. So, it worked, sort of. I mean, my little Terran Marines were holding their own, I'll say that much, but we didn't get very far in terms of complexity, so I'll say that. And so let's see. Nairi, you say you're self-studying from 0 right now. Okay, well, and Snakebite, you say you're self-learning too. I'm so happy because y'all, like my background, my undergraduate education was in North African linguistics. I went to graduate school for a couple of years and then left. I'm self-taught entirely. My programming, my software development, my computer science, my machine learning, all of that. All of it is entirely self-taught. So I'm here. It was funny. I got asked at work recently. I got a raise and I'm kind of entered into like the area of my career where I need to like start building a team. And so my career manager, who's like the person who kind of is supposed to be your career mentor, was like, I really want you to start thinking about what kind of people do you want on your team when you're building a team for yourself. And like it came to me instantaneously. I was like, I want self-taught people. Because he was talking about recruiting from colleges and everything. And I was like, but the most brilliant, passionate, interesting people are the ones who either do or don't have a college degree. And if they do, they've changed careers or they've started to teach themselves things. And those are the people that I really want on my team. Because I don't know, there's something about people who are self-taught. Like I'm biased, but like we're a special crew. We know how to learn things, and I feel like that is an underrated skill, because especially like in my job, I'm often put on projects where I don't know at all the subject matter, and I have to, in the matter of weeks, teach myself enough to be able to start building models, start building software to do pretty complicated things. And it's not it's not my education that helps me. It's the ability to just dive in, go, what do I need to learn? And start learning it. And self-taught people, like, we can do that pretty well. So I'm all about self-teaching. So I'm glad that you all are here. Questions are welcome. So please, any tips? What was the best resource? Depends on what you're learning. So thank you so much, MK Wendo and Okabe, for following. Welcome to the stream. Can you hire me? Maybe. Hit me up, Generic Crew. Let's talk more. No, step 1 is not be super smart. Step 1 is just be really, really curious. Step 2 is be really, really stubborn. I can't tell you how many times I've sat there reading a paper going, yeah, I didn't understand a word of that. All right, starting over, read it, and like every third word I'm having to look up. If you're stubborn enough, eventually you're going to understand that paper. So a combination of curiosity and stubbornness totally beats being super smart. I promise you. And let's see. Undergrad was in astronomy. No, that was my graduate school was for astrophysics. But okay, back to the code. I will try to chat a little bit more at the end, but I also want to make sure that I get through this. Okay, so let's first take a look. After we have this, let's compare our predictions with the actual labels. So what we're going to do is we're going to take this little ypred. It's just our predictions, and let's have it. Say, hey, predict. Right, we're not using our training set, we're using our testing set. So this is not what our model is fit for. And oh, thank you for following, Nairo. And let's see what it looks like. All right. And because I'm lazy, I'm going to copy my matplotlib scripts. All right. No, these aren't prices. This was from something else I was doing. Predicted. No, these are prices. Okay. No, I did that right. Good job, me. Values, home values, whatever. They're like the prices of the homes. Not bad. So these are the actual prices. And this is what we predicted. And a perfect model would have that y equals x perfect line all the way through. We don't quite have that, but you know what? It's not bad. It's not bad. It's good enough for government work. All right. Favorite star in the galaxy. No more off-topic questions just for a little bit. I got to get through this. But then, favorite star. That's tough. Okay. So, our next thing that we're going to work on. Okay. Yes. Thank you, Loafbone. All right. We're going to go through something called k-fold cross-validation. Wow, lots of fancy terms, right? So hold on. Let's go back to our whiteboard briefly. Clear our canvas. Because I don't know, I'm a very visual person sometimes. Like when it comes to, I find that teaching people visually seems to work the best. So, move my little tablet over. All right. So k-fold cross-validation. Fancy words for a simple topic, I promise. All right. So this is a method for resampling our data, and it's used to evaluate machine learning models and also to avoid that overfitting problem that I told you about earlier. You might hear it called sample testing, but at least in the machine learning world, I hear it. Sample testing I've heard more from people who were statisticians. Pardon me. But k-fold cross-validation is quite frequently used in, that's the term used in machine learning at least. And it's really easy. All right, we're going to follow a couple steps here. Step 1. We're going to shuffle our data. Step 2. We're going to split it into k groups. By k, this is just some number. Okay, we're just using k to mean some number. We could do 5, we could do 8, we could do 20, we could do 500. Is that XGBoost regressor? Yes, generic crew. I have, briefly. And then, okay, we're gonna pick one of the groups. Then that group is gonna become the group that we just picked, is gonna become that test set. So we're gonna hold it out, we're gonna remove it, right? We're going to pull it out of the data. We're going to fit model on the rest, right? Because that's just our training data. I hope you can read my handwriting. And then we're going to test on the set that we've held out. Then retain the score and start over. Okay, so what this actually looks like is, and I wrote way too big, so we're gonna have to clear this. I will in a minute in case I doubt anyone's taking notes, but if you are, I'll give you a minute. We're gonna shuffle our data, we split it up into a bunch of groups, hopefully about equally sized. You're gonna pick one of those groups, you're gonna pull it away, you're gonna train on the rest of your data, test on the thing you pulled out, then you're going to do it again. And so maybe that one that you just held out joins into the mix to be trained on, but another one gets pulled out to be tested on. And so there's a lot of like really pretty pictures. I'm not an artist, so this is going to be really ugly, so bear with me. Clear canvas, please. Thank you. But so let's say we have, I love this film. Look at it, it's so sparkly, it looks like stars. All right, let's say this is our data. And we're going to split it into however many groups I can fit lines. So 1, 2, 3, 4, 5, 6. Okay. So in this case, this would be 6-fold. Normally it's 5-fold, whatever. 6-fold cross-validation, okay? And also, Dataticus. I'm going to be putting the code on GitHub, and once I can proofread it and make it pretty and not as ugly, I will also be putting my notes on GitHub as well. Because I have a bunch of notes that I'm talking from as well so that I don't get distracted. But I'll be putting the code first, and then it might take me a little bit longer to clean up the notes. But then I think you can use the GitHub command, Mark Zuckerberg. There isn't much there now, mostly teaching stuff. So the vast majority of like my fancy code, unfortunately, is on. Oh, here you go. I got you, friend. Hold on. There you go. Thank you, generic crew. What was I saying? Oh yeah, the vast majority of the nice code that I use. Oh no, I can't sneeze. I don't know. I'm staring up. Sometimes it works. It helps me not sneeze. Okay, we're good. The fancy software that I write for work obviously is on an enterprise GitHub, and the stuff that's on my personal GitHub is mostly things that I use to teach or like do tutorials or things like that. I'm hoping to make my personal GitHub fancier, but that requires working outside of work hours to have like passion projects and everything, and sometimes I just like playing video games. So anyway, to explain 6-fold cross-validation, let's say we're gonna remove this. This is gonna be our test. We're gonna test on 1 here, okay, and then 2, 3, 4, 5, and 6. This is our training data. Okay, so then we test, we train, whatever, we get some score. Let's say our accuracy here is 0.68. Now, we're going to do it again, okay? But this time, let's pull out, this should probably be red, whatever. We're not being consistent here. No one cares. Now 2 will be our test, and we'll train on 3, 2, well, no, shoot. Let me go in order. I'm organized. 1, 3, 4, 5, and 6 will be for training. Maybe this time it's 0.71. And then scratch the top of your nose and sneeze. Also, it makes me look really, really weird, but like you have these bones, right, that are like right here. And then, at least in my nose, there's like a little bit of a notch, like kind of indents right around that bone. If I push there, I won't sneeze. So if you ever see me like, especially in like conferences and stuff, and I'm sitting there like squeezing my nose, I'm trying not to sneeze. I have really bad allergies, so I'm sneezing quite a bit. Ooh, thank you so much for redeeming Hydrate. Got to open another sparkly beverage. Okay. And so forth. And then at the end, these become our scores. And often I like to look at the average of them. The lights are not on right now, okay? And so maybe someone else can help me, when some other like that's more pro streamer can help me figure this out. But I have a green screen now. Thank you, Stream. Stream donations making it possible. I love you all. But I have these like programmable LEDs that people were really enjoying being able to program. So they're like a rainbow, and there's all different kinds of things that happen. But because I have a green screen, all of the LEDs mess with the green screen. So I haven't figured out a way to have the LEDs still be something people can program without it. Maybe I could put them near the Furbo or something, so the Furbo cam. I'm not sure. I haven't quite figured it out yet, so I'm sorry. Savion Demarion, thank you so much for following. And Shy Ryan, I might have missed your follow. If I did, I'm so sorry. Thank you for following. And Super Negasonic Teenage Warrior green screen thingy. I know, I love my green screen. And thank you, Strawberry Jesus. The first hour of this stream was covering the basics of linear regression. So we went all the way back to y equals mx plus b and talked a little bit about what linear regression is doing, a little bit of the math behind it, and why linear regression is so great. And now we are actually coding, but I wanted to take a brief, small tangent to talk about k-fold cross-validation so people could understand it. Before I move off this blackboard, whiteboard, whatever, are there any questions about that? I think it's pretty intuitive. Like, you're just kind of selecting different groups of data to hold out. And no, can you redeem? Hold on. Can you maybe turn those off? So there are some streams where I don't use my green screen, and then we'll have the programmable LEDs up for all of you. But I turned them off tonight just because they mess with the green screen. And it took me way too long to figure out how to get the green screen to actually work. So the scores. So the scores here depends on the model, but here they're kind of like, you can think of them as a measurement of how accurate. And I'm going to use that for now. Those of you who are statisticians or already machine learning people, I know what you're thinking. Hold. We'll talk about different ways to evaluate models probably in tomorrow's stream. But for now, you could think of it like a measure of performance. Like, that's the grade of the model. So it's getting like a 68% or 71%. My main question is how you decide exactly on the number of folds. So this is actually really, really, really interesting, because I was experimenting with this the other day and noticing massive differences in average scores between different choices for K. So I looked it up, read more about it, and there's lots of wonderful math explaining that the best selections to avoid overfitting are 5 or 10. And so it can depend on the size of your data and the complexity of the model. But generally speaking, you're going to want to stay with 5 or 10. 6 is only because I drew it badly. So we only have 6 in this particular case because I'm bad at drawing. But normally you're going to usually want to use 5 or 10. 6, yeah. It's literally just me. I tried to draw 5 and there was an extra 1. I'm bad at this. What is a fold? So in this case, you can think about it like, I would say like it's a group, essentially. So that's the number of times that you are going to divide your data. So like K group cross-validation. You can think about it kind of like that. And no worries, ONAD, that's totally fine. All right, so let's return to our code now that we know what k-fold cross-validation is. The other reason that we might want to use this is all we did before, right? Was we took 30% of our data, we held it out, trained on the remaining 70%, tested on that 30%, and we called it a day. That's not necessarily giving us the most accurate performance on our model. We're not shuffling our data. So if there's any kind of pattern in how the data is listed, our model might be picking up on that. And also, we're not testing it repeatedly. We're only kind of doing one prediction going, oh, how well did we do? Let's see. So while yes, I agree, oh, isn't it so nice how well our model did? We should be very suspicious of that number because we only did it once. We didn't do any kind of cross-fold validation or k-fold. I hate that. Can we have a simpler word? Cross-validation is usually how I hear it said. But anyway, we didn't do anything more complicated, so we should be suspicious. And Okabe, you say, what does development set or dev set mean? Is it the same as test set? So for at least in terms of machine learning, usually you're going to hear like training set, testing set. You'll also hear, oh my God, brain. There's another term, it's not development set, but there's another term that's used because we need to sometimes distinguish, and this is kind of what I was getting at earlier, if you remember the validation set. Thank you, Jimbo Jones. Oh, calc math. You people are wonderful. So to hear like Bueller, brain, and all that's in my head is like Christmas music, because I've been listening to it all day. Oh, speaking of which, we lost our music. So 1 second. Let's keep having our little like DMCA free Christmas music for Twitch. Okay. Got to keep that going. Got to keep in the spirit. But it also means my brain's a little full of other things. Brain.exe, stop responding. It's me a lot of times, unfortunately. All right. But so for a dev set, I haven't really seen that used. I don't know. There are also different conventions across different languages and also different countries. And so there might be some differences there. But dev set. When we're talking at least in terms of, yeah, so calc, that's what I was wondering. Well, development though, it might just be local jargon to Mayakosa's point. But also I think this is why terms need to be a little more normalized and standardized because it really helps us all communicate better. But we will be talking about, so today we're just starting with test, train, split. We'll be talking about test, train, and validate a little bit later. But perhaps it is just, you heard it from Andrew. Really? Then it's got to be like, what context did you hear it in though? Was it in the same context as like test, train, set? Because now I'm actually kind of curious. Hold on. Let's see. Andrew. Because I've heard a similar term used. Okay, so. Yeah, the validation set. Sometimes also called the development set or the dev set. Huh, I've actually never heard anyone refer to it as that. Validation one I've heard a whole lot of people use. But that's cool. That's good to know. Terminology can also differ, I should warn you. Unfortunately, there can be pretty big differences between terminology used in academia and in industry. And so I wish it weren't the case, but there can be sometimes a split there and it can get a little confused. Okay, so, all right, you say, so I may have missed this, but basically we found the best fit line for the train data, then tested it against the test set, right? I'm a little confused about where the model is or how we're going to refine it. Okay, so the model in this case is, we'll go. So it's right here. So it's actually, we're using the linear regression class available from scikit-learn. And then we fit it to our training data. And so within that particular class, that model, if you want to think about it like the equation for that model is stored in the class. And then we can call various methods from the class like score or predict to use what that model has learned to make predictions. We're going to refine it in a bunch of different ways, but pretty much it's stored within that instantiation. That object, the linear regression object that we've instantiated from the class is storing it. Yeah, no, you're fine. Totally cool. We kind of breezed through this a little bit, so no worries. All right. No, and also, you know me, you can ping me on Discord for notes if you need it. I'll give you my ugly notes if you want them. But the code will be available on GitHub. So, okay. So now let's see. Let's use our cross validation score. All right. We've got X, we've got Y. And we're gonna, for our cross folds, we're gonna do 5. Anyone want to make a prediction? What do you think? Is this gonna perform better or worse? Is the mean of our cross validation score is going to be better or worse than what we just saw? Get ready. Because even I was like, oh man. Better. Ooh, Onad, why do you think it's going to perform better with cross validation? I'm curious of your logic. Lovephone guesses worse. Okay. If stream polls were working, we could do a stream poll, but stream polls like to be horrible. Worse, yeah. Are you ready? Have you prepared yourself? Oh. Ouch. That's bad. So we went, oh, thank you for following Rihan PG. Yeah. I know, right, chat? We went from happy land of isn't this so great look at our amazing model. We're so great. 76% accuracy. Yeah, let's ship it to the client. No. Nope. So, a couple things are going on here. One, and I kind of learned this. I learned this the hard way. Let me see. Hold on. Learned this the hard way. Remember like literally 5 minutes ago when I was telling you that standard cross-validation, you shuffle your data first, right? It's like, duh. Well, guess whose cross-val score method doesn't shuffle your data? Thank you, scikit-learn. So it's not shuffling the data, which could be a massive, massive problem. So we're going to redo this, but we're going to be really, really, really intentional, and we're going to make it shuffle our data. Okay? So instead, we're going to use something called shuffle split, which is going to say, I want you to do 5 splits. We already talked about that. Move this so you can see me. And I want... I don't think we really need this, but it's fine. And we're going to have random state. All right. Now... Oh my lord, I can spell. Do you think it's going to be better or worse? I love playing this game. What is your evaluation method for score? So in this particular case, I do believe that it is using... It's just doing ordinary least squares linear regression. So it's just doing kind of what is considered standard. We can control that. So we can change the evaluation method. But for here, I'm sticking with the normal one. We'll talk more about evaluation methods coming soon. Better because I smile this time? You should know me better than that. Not as good as before, but way, way better. So again, the importance being shuffle your data. Shuffle it. Especially if you're dealing with data where you think there might be some kind of sorting that's happened in the data, or maybe you're dealing with like time series kinds of data, so where things might have a chronological order. Shuffle that shit. Shuffle it. All right. So ways to improve this. Now, I'm going to put a giant caveat here, okay? Which is that this particular data set has been normalized and pruned and filtered and made as best as it can be because it's a classic learning data set for machine learning. So not a lot of the things that we're going to do is actually going to make it better, but I want to show you how anyway. Unless chronological order matters. Exactly, Strawberry Jesus. But we're not doing time series yet. And so the reason I want to show you these things is even though we have this beautiful data that we're working with that seems to be so wonderful, most of the data that you are going to work with is going to look nothing like this. It's going to be a hot mess. So I want to show you some techniques for how to make it better. The first one is going to be normalizing your features or standardizing them. And this is because if you think about it, if you have features that have vastly different ranges of values than other features, that can really, really, really affect the model, especially if those are extremes. And so it can almost make the feature look more important or less important than it actually is because it just has an integer value or a float value that is way different than the rest of the data. And so we're going to be using something called standard scalar. This normalizes the data by removing the mean and fitting. So we're going to say, in this case, our x values. This is a handy little like back of the notebook way for myself that I can remember if I standardized my feature vector is I capitalize the x when I've standardized it. So it's a shorthand for myself unless I forget to do it, but usually I'm pretty good. Where I can immediately look at an input to a model, like here, And see, I haven't normalized it. So feel free to copy that if you wish. Let's see, it's standard scalar. All right, so now we're going to be using the standard scalar, and we're going to give it our feature vector and say, normalize this, please. And so I'm not expecting to see a huge difference here because this data is like really, it's pretty, it's nice data, but we might see a small change. Oh yeah. Like 10 decimal places, but whatever. There's a difference, okay? Still, like I said, I have seen this make a massive difference in a data set that was not perfectly cleaned and like set up. Like seriously, the Boston housing data set is a great teaching tool. But one of the flaws that I would say with using this and like the Titanic data set, which we'll be using tomorrow, they're great. They're like hallmarks of learning machine learning, like the Iris data set, whatever. But the problem is that they're so perfect. They're too perfect. So they're great when you're learning what a linear regression is. But the second that you like step out into the real world where the data is like the equivalent of someone's like chewed gum underneath your seat, it's a lot harder. And so I want to show you these techniques because they're not making a big difference on this already wonderful data set, but you're probably going to need tools like this, and you should just seriously normalizing your data should just be, you should do it. Just do it. Just do it. Trust me. But it's a good idea to kind of have these tools in your toolbox because most data is very nasty. Okay. So the other thing that the Titanic was an inside job. Okay. The other thing I want to talk to you about is another fancy word. All right. But it's called multicollinearity. All right. Let's actually, you know what? Let's go back to our whiteboard and let's break that down because that's a word. That is a whole frickin' word. I hate sometimes how inaccessible some of these terms are. It's like, there could be so much of a better word for it, and I'm not good at coming up with those things, but guess I could probably come up with something better than multicollinearity. I don't even know if I'm spelling this right. Probably somebody will come and be like, actually, that's not how it's spelled. So, multi, we're dealing with many things. Co, those things are together. Linearity, they have a linear relationship. So what we're getting at here is that you can have problems, serious problems with linear regression if multiple of your features have linear relationships with each other. So, I'm not writing with a mouse, my friend. I am cheating. I have a stylus. And that is also a thank you to chat for giving me wonderful donations that allowed me to afford this tablet, which is making you should have actually seen my mouse writing. It was horrific. And now this is allowing many things like this wonderful machine learning stream and also future Math Monday streams. So if you like math, stay tuned. Also join the Discord because I think I need to make a Math Monday channel because I'm kind of like in the info gathering phase for Math Mondays where I'm trying to figure out what people need the most. So get excited for math. In any case, multicollinearity. So think about this in this way. Let's go back to our temperature example for a second, right? So if we have, right, in that example, let's use purple because purple's pretty. Our Y here is the weather. That's what we want to predict, right? Okay. And then our X values might be things like temperature. Ooh, those are straight lines. Humidity. Pressure. Let's add in time of year. latitude. So this might be great, right? Cloud cover. You want cloud cover? Let's add in cloud cover. Can you still see this? All right, this is, I guess, is like reaching sort of towards my head, but that's fine. Cloud cover. Okay. Wow, this is great. Okay, we have so many variables now to predict the weather. Well, what happens? And also we're gonna suspend some judgment here because I have to make this work for proving a point. But let's say that we live in a place where the time of year, like our place, we always, like, I don't know, maybe we're in California where it feels like it's 70 degrees all year round, okay? But maybe the time of the year and the temperature, there's a really strong relationship here. And thank you for following Numentar. Maybe it's even, maybe it's even a linear relationship. And maybe, I don't know how this works. I don't even know really pressure. I remember learning with like hurricanes. But let's say also that, you know, latitude, okay, no. Let's say there's also a linear relationship somehow. We live on a magical planet, all right, between latitude and humidity. Well, what happens here is that it's probably not a perfect linear relationship, but when you have all of these interrelationships in your data, you're actually overcomplicating your model. You're saying, hey, this is important, and this is important, and this is important, and this is important, when if they have a really linear relationship, we might be able to say, actually, you don't need these two. I don't know why it makes the eraser so big. That stresses me out. But because we wouldn't really know. We have all we need to know from temperature and humidity because those are linear related to the other variables. And then you can get serious problems. So one of the things we need to check for this multicollinearity is very easy thanks to pandas because, oh shoot, what did I call our data? Way back at the start? Data. Oh, good job me. What an excellent name. We can look at the correlation matrix. Woohoo! Get excited. Okay, so for all you programmers and smart people out there, my question is, why do I keep seeing welcome to chat or connecting to chat all the time? Ooh, I don't know. I'm sorry, I can't help you with that. I wish I could help. All right, so what the hell is this giant bunch of numbers, and why is it important? Thank you IK1CK3R for following. So what we're looking at here is this is the correlation coefficient. Fancy word. Think about it as the strength of that correlation, the strength of the relationship, the linear relationship between two of these variables. So we can look at something like, oh, say crime and crime. Duh. It's going to have a perfect relationship with itself, obviously. But so what we might want to do is we might want to look through here and see what, say here. So we've got tax and rad. I'm trying to remember what those are. Thank you for following Shadowmore. So we got tax and rad are like 91% correlated. The accessibility to radial highways and the full property tax rate are very linearly related. So where was that? That 91? Here we go. So pretty much when I'm doing this, I'm looking for anything that's like upper 70s plus. And you have a lot of different choices here. You can drop the variable and be like, you know what? Nope, I'm not going to use this at all. I'm just going to... data is a pandas data frame. So we just used scikit-learn's load datasets to bring in the Boston housing dataset. And we put it into a pandas data frame. So when you're looking for multicollinearity, this is a great way to do it if your data is in a pandas data frame. Because you can just see all of the correlation coefficients right here. And you can kind of explore a bit. It doesn't look like we've got a lot of it. This is the only one that really stands out to me. Let's see. Do we see any others? Also can show very interesting relationships between your data. So this one is very intuitive. Look at this. Age and the nitrous oxide parts per million. So something about like older homes, greater amounts of nitrous. I don't know anything about nitrous oxide parts per million in houses, but there's a relationship there. Same with, this one is very obvious. Proximity to an industrial zone and the amount of a particular chemical in the air. That makes a lot of sense. So what can you assume from that high number? What we can assume from this high number is that these variables, RAD, which was the accessibility to radial highways, I don't even know what a radial highway is very, very strongly correlated with the tax. That's why I have a data dictionary, my friends. The full property tax rate per 10K USD. So higher tax rates if there's greater accessibility to radial highways. And Mopor Cam Crusher, I love your name. You say also older houses are near industrial areas. So let's actually look. Age and Indus. So there is a positive relationship there, not as strong as some of the other ones that we've seen. You remember homes of younger people, teenagers. Phew, no. In any case, and no worries, generic crew, get some sleep. Thank you so much for stopping by. And I think probably Loafbone has convinced me to put it on YouTube, so we'll have that available. Nevertheless, you have decisions to make when you see strong amounts of multicollinearity. Freaking word. Why can't we have easier words? Multicollinearity between our features. And so snakebite, you say, what about negative correlations? Well, that's the beauty of this correlation matrix, is that wherever there is a negative, it'll be a positive somewhere else. So they will be echoed. So we have this Indus being positively correlated with Nox. So that should mean if we go to Nox, oh no, those are the same. So what was the negative positive switching that happens sometimes? Did I just make that up? I might have, no, see, it was the same, hold on. No, there was, yeah, so they do, if you have negatives, let me just rephrase. Also, quick aside really quick about collinearity before I forget. You also really, really want to pay attention to what is strongly correlated with your predictive variable. So here we want to predict MED-V, and it looks like LSTAT has a really strong correlation, negative, but still a strong inverse correlation with that particular, with that variable. So I'm trying to remember what that actually is. LSTAT, the percent of the lower status of. So, I mean, that kind of makes sense, right? Generally speaking, poorer people can't afford higher value homes. Yes, Numentar. So I know what you're talking about. You're talking about heat maps, and I can do it in Matplotlib. It just looks really ugly. I love Seaborn's heat maps for this, but Seaborn shit the bed. And the data is standard scaled. Yeah, so VLL's already, I think it was already scaled, but as I mentioned earlier, I wanted to show people how to do it because 100% of the time, you're going to be getting data like in the field that nobody's scaled before. Like most of the time, the data that you're working with, I would almost venture to say all of the time, if you're getting raw data that nobody's messed with, it's not going to have these wonderful pre-processing, cleaning things done to it. So you should know how to do them. Seaborn is beautiful though. I love Seaborn. But it was being a poop face before this, so I decided not to use it for today. 1K, we'll get there. This is day one. For most people, this is the first machine learning they've ever done. So we're not jumping straight into autoencoders and principal component analysis and things like that. So hold your hats, my friends. Okay. So here are a couple of ways that we can deal with things like multicollinearity. Like I said, you have a choice. You can just drop it and redo your linear regression and see what it looks like. I prefer not to drop it, but to kind of make the model decide. And how we do this is something called regularization. I know. Ugh, more terms. But we're going to briefly go back to our wonderful whiteboard, blackboard, whatever, so that I can explain this. So do you remember all the way back at the start of stream when I was telling you that we're going to be using this kind of like sum of our squares for error? That is my fountain pen, not the pen I need to use on here. Okay. So we're just going to abbreviate that. Oh no. RSS. Right? And this is the thing that we are trying to minimize. This is our loss function. You can also think about your error function. We have a million terms for the same things. This is what we're trying to minimize. We don't like this. This is a measurement of how bad we're doing. So whenever we're trying to fit that line, right, that whole fitting process, the training process for a machine learning model is all about minimizing this loss function. So we have two different kinds of regularization, okay? Our first way is something called Ridge regression. You can also hear it called L2 regularization because, again, we need 500,000 terms for the same thing. By the way, and I had an interview, I had a technical interview, where they asked me the mathematical difference between L1 and L2. I swap these all the time. I don't care if you call them Ridge, Lasso, L1, L2. I swap which one's which every single time. And I remember just sitting there. It was like, it was an 8 a.m. interview, 9 a.m. interview, but a 3-hour time difference. So 6 a.m. for me at a conference. I was exhausted. It was like the 4th day of the conference. And they're like, oh, well, can you explain mathematically the difference between L1 and L2 regularization? I was sitting there like, I'm sleep deprived. The only thing on my mind is like Lagrangian points. I was like, I know how to use these things. I've used them a bunch of times. I'm tired. Can we get coffee? That was rough. I was like, oh my God, this is like almost 2 years ago now. Anyway, so each of these regularization approaches, and you should remember this, don't be me, don't be embarrassed, caffeinate yourself before interviews. Both of these regularization methods are going to add a penalty term to this loss function. They're going to add something extra that our model needs to consider. So in this particular case, don't worry so much about the math, but I'm going to put it here because I know my math geeks, of which I am one, will love it. Okay, really though, all this is getting at, this is kind of like, you can think of it almost like a learning rate, sort of. Tuning parameter would be a better way to say it. Like, it's later, like alpha you'll see a lot used as a learning rate, but here it's more of like and by tuning parameter, we literally just mean, it's like a constant that just does stuff. Tune it. This is your number of features, so your number of x's, your number of inputs, we'll say. And here, this is our coefficient. And so this, if it's small, if A is small, there's no penalty or very little penalty. But as alpha gets much, much bigger, it starts to penalize our coefficients and it shrinks them. And then we also have, and we're going to go through practically what the difference is as well in a second. Lasso, or L1, I guess I did these backwards. I always think of Ridge first, but I don't know why that is. Thank you. Oh my gosh. Thank you so much for the gift subs, Loaf Bone. And now Jan, here for Chess Vids, High Altitude, Cherenkov, Grateful Tomato, and Dr. Jekyll, Mr. Hyde. Now you're stuck with me. So now you have subs, you have cute little emotes of my dog. Welcome, welcome. And when the lights are back working, when we're not doing a green screen stream, say that 5 times fast, you get free use of the lights. So have fun. So this is our regular sum of squares. So if you remember right, almost tried to go back on this as if we have our as if we have our I have the notes from earlier. But this is our, remember when we were talking about squaring the error and adding it up? That's what this is. So this is just that sum that we were doing earlier where we're taking the difference between the prediction value and the actual value and we're squaring it. We're adding it all up. That's what this is. An abbreviation for our loss function in this particular case. Okay, and so then this one, can you still see this? Yes, okay. Just making sure you all could see this. Okay. It is really, really, really imperative that you normalize your features before doing regularization. And so, if you're, okay, you say, how does Lasso deal with correlated parameters? If you're worried about correlated parameters like multicollinearity, I would say use ridge regression, not Lasso. So Lasso's a lot better if you have a really sparse input vector. And so what that means is there's a lot of zeros. So this might be the case. Here's like a nice rule of thumb that you can think of, is if your x's, your input data, were categorical, so you had to do any kind of encoding, or you have, your feature vector looks like a lot of zeros with some ones here or there, and we'll talk about encoding and everything, probably tomorrow actually, if I have time. If you have lots of ones and zeros, think about using Lasso regression then, because Lasso works really, really well with a sparse vector. That means lots are zeros. Oh my goodness, and thank you so much, Rug Devil and Remarch, for following. It also works really well if you're like, I don't really know my data that well, so I don't know what features are relevant, so I'm just going to cram in all my possible features, and I'll let the computer figure out which ones are important. Lasso then is the regularization for you. If instead you're really, really concerned about multicollinearity and like those correlations between different inputs, then you want to use ridge regression. The best, often in my case, I found is something called elastic net, which combines a proportion of ridge regression with a proportion of Lasso regression. Combines them for more fun. So let's test both of these out and see what happens. So we don't really have like a sparse feature vector, so we're probably thinking in our minds that we want probably ridge, but you know what? Also, sometimes the data's weird. So let's see. Let's get model. Okay. And so how am I doing on time? All right, 2 hours. All right, I'm doing all right. I told myself I wouldn't stream too much longer than 2 hours, and we are almost done. So I wanted to leave a little bit of time for questions too. But all right. The other thing that we're gonna do really quick is we're gonna, for that value that we were just looking at, this alpha right here, we have to tell the Lasso or the ridge regression in scikit-learn what alpha to use. How the hell do we know what alpha to use? We don't. Let the computer figure it out. Duh. So in this case, we are going to pick, we're going to pick some alphas. We're going to pick a whole range of alphas. And we're going to say, hey, computer, here's the alphas I want you to check. What was the best alpha? So it will go through and test these alphas for us. Now, oh my goodness, thank you so much for subscribing, Numentar. Thank you. And hot iced tea. That's confusing, but welcome nonetheless. Where did I learn Python and what are the best resources to use? I taught myself Python, actually. And I would say there's a million resources out there for learning a language, learning the bare bones, learning like the syntax and everything. My best advice to you, Mississippi dog, is practice, because it's easy to watch tutorials. It's easy to do Code Academy and have your hand held a little bit through some examples. It's a lot harder to sit there and go, oh God, I have to code this myself. Like, how the fuck do I do this? Okay, and then you have to figure it out. So Advent of code is great if you have a little bit of some programming experience, but you want to kind of flex and try out some challenges. I found that the Advent of code is really fun. Not many people, well, lots of people know about it. I didn't, so I'm spreading the love. But the biggest thing, honestly, even if sort of the esoteric coding challenges aren't really your thing, the thing that I've loved the most is just getting passionate about a project, finding something really cool that I want to do, that I want to code, that I want to figure out, and then figuring out how to do it. Thank you, the Sharp Spoon, for following, because it's gonna be a lot easier for you to keep up your motivation and your passion if you're actually interested in figuring out how to do it. And yes, Strawberry Jesus, the coding notebooks will be available very quickly on GitHub. The notes that I've taken, I need to clean up because right now they have lots of large notes to me to like pay attention, don't be an asshole, things like that. So once I clean them up and I remove them, I make them look pretty. I wanted to add some additional links and pictures and stuff. So once I kind of enrich them a little bit, I will have them out there for you also on GitHub. But this raw code that we're just going through together, that'll be available after the stream. And Goofy Lagrangian. Ooh, I like your name. Welcome. Thank you for following. Okay. So, what are we doing? All right. So now let's get our ridge regression going. That's not how you spell ridge. Okay. So now, oh my Lord. Whew. My GitHub name is the same as Twitch. Yes, one only match. You can also just use the exclamation GitHub command in chat, and you should have a link right there. The caveat that I give everybody when they go there is that this is not my main GitHub. This is the GitHub that I'm allowed to share with the public. So I usually use this GitHub more for teaching. Okie doke. So it looks like it had less of a good performance, which, like I said, this data is really, really, really well. It's well processed already. Also, we could just like be, hey, let's search for some more while we're sitting here talking. Let's let it chug for a second. And let's see if maybe like our alphas weren't accurate enough. No, it's about the same. So we're not going to do ElasticNet tonight, but I will say that when I was writing these notes, I thought about if I were doing this, I would try ElasticNet, not Ridge versus Lasso. But where do I run the codes? Do I have an AWS account or Google Colab? Oh, hey, hi Matt. Okay, yes. Yeah, okay. Well then like everything's on my work GitHub. Like I feel like that's like the eternal bane of so many of us like working on those technical projects is we build the cool software and they're like, shit, I can't tell anyone about it. So yeah, that's why my GitHub looks a little sparse. And Goofy Lagrangian, this code is all being run locally on a Jupyter notebook. It would be overkill to do something like an AWS account for something as small as the Boston housing dataset. I will think about it for some of the heftier streams. I think probably what I'm going to do is just probably we'll work with, for like the deeper neural nets and some of the bigger models, we'll probably just work with a pre-trained model, because training can take days, my friends. It can take days and days and days. Jupyter, how is it in the dark theme? Oh, friend, I have magical ways. No, I will, hold on, I will get you a link. So Jupyter Notebook themes are absolutely possible. I'm giving away all my secrets. Here you are, Rhythmia. Enjoy. It saved me. Remember ARM, the kind is the process of applying for a couple of patents. Oh yeah? Okay. That was an interesting project, I have to say. That was an experience. One of my first experiences with... I had been working at the company I was working at for like 6 months, even less, and I was put on that project, and they were like, we want an independent tester for our software, and I was like, cool. Then they're like, but we're going to wait till a week before the deadline to give you a laptop, and the code's not going to be ready until the day the testing report's due. And I was like, okay. Oh, thank you so much for subscribing, 1K. Thank you. Yeah, exactly. As you were building it. So like, this is no blame on you all, but like they brought me in and then they were just like, well, we expect a testing report like in a month. And like 2 weeks before the testing report was due, it was like, here's a laptop that can have the client data on it. And here's our report that says what we're hoping the software is going to do. A week before, I'm like, yo, like, when can I test this? Oh, it's not ready yet. Okay. Like a day before the report's due, I'm like, guys, I need it. It was such a clusterfuck. And I actually, I don't know if you know this, Matt, I had to cause a little bit of a kerfuffle because, oh shit, but if this shit's on YouTube, I can't talk about this. God damn it. Okay. Anyway, I'll can I crop stuff? Can I crop stuff off the VOD? No, but this is in the middle of the learning. Okay, Matt, we'll talk about this in the later segment. Once I'm done with the learning, maybe I can like crop out the last like 30 minutes. But I gotta tell you about like the shitstorm I had to cause because of that. Good Lord. Okay, all right, so we're gonna try some lasso regression. Anyway, okay, I haven't done any VODs. I just like, Twitch puts them up and I'm like, it's fine. I don't really deal with the VODs. I don't even know if I have a YouTube channel, so. All right. So same thing as with the ridge regression. We need to figure out what alphas we need to use for our lasso. And so in this case, the syntax is a little bit different, but we're gonna just say, hey, search for 100 alphas for us, please. Find me the alphas that work. And so we're gonna use whatever alpha this comes back with. And then let's do our lasso regression. You call it lasso, I called it L, didn't I? My goodness, Jess, all right. Don't be like me. Be more consistent in your naming. So better than the ridge. And that's why, honestly, I would probably use a combination of them both with elastic net. If I were to go about doing this. But again, sometimes like a lot of this isn't necessary because our data is already wonderfully balanced and cleaned and perfect. Let's see, the pre-training. Yeah, exactly. So that's where if your local machine can't handle big data sets and you don't want to shell out for the money, you can use a pre-trained model. But also that's why sometimes these simpler models are really great, is because you got to figure, you got to be able to learn and code it yourself and whatever. And thank you, Hector HSC, for following. So this is a good introduction to linear regression and some of the hyperparameter tuning methods. So that's really what we just did. Some of this is about tuning those hyperparameters that you might hear people talking about. And really that is just like, we're tuning our model. We're trying to make it better. We don't want to just do what we did at the beginning and use the linear regression right out of the box. And so I think a couple of things to remember with linear regression is that remember your different kinds of regularization for sure. Please remember to always scale your inputs. Remember that it's based on an assumption. It's based on the assumption that you have a linear relationship between your inputs and your output. That might not be true. If your model is failing, if you're just stuck and no matter how much you tune it, you're like, man, you're massaging this thing to death and you can't get above like a 50% accuracy, which is like a coin flip. Well, maybe it's because you have the wrong model. You say, does it select the best alpha or use an array of alphas? So the CV is cross-validation. It's doing cross-validation, but with different alphas to choose the best alpha. So the alpha that performed the best in the cross-validation. And thank you, Benubo, for following. And the other thing to remember is that linear regression is what you want to use if the thing you want to predict is continuous, right? So tomorrow, what we'll be talking about is logistic regression, which is what you want to use if you have a binary label. So win, loss, yes, no, up, down, etc. But if you have, like in our case, a price, and you have a whole range of prices, then linear regression is a good place to start. And yes, arrhythmia, that's why I wanted to start with linear regression, is I know everyone wants to be here for the neural nets, but like, we can't get there and start talking about gradient descent and calculus and like all of that business until we've talked about linear regression. Also, I know this is going to sound maybe a little frustrating to some of you, but when it comes between a linear regression, a well-tuned, well-trained linear regression, and a super fancy deep neural net, which one do I use more? I've used a linear regression far, far, far more. And obviously it depends on the problem. Like there's certain kinds of problems like computer vision that are always going to need a little bit of like a heftier model. But don't give up on your simpler models that you learn in the early days, because they're explainable, they train fast, they're really straightforward to tune and to interpret results, which is great if you're working with non-technical people and you're trying to explain your model results to them. And sometimes simple is best. Oh my goodness, thank you. You like my headphones? So these are the Bose Quiet Comfort. I love these so much. Like, I could wear them all day long. They're the most comfortable thing. And they're noise canceling, which if you're like me and maybe you're easily distracted, the noise canceling, these are my babies. I have like little adapters so I can use them with my Switch, with my computer, with my work computer, with my phone, like everything. I'm just like, I need them with everything. I love them. Thank you for following, Choka. And so, with that, my friends, we are kind of wrapping up with the linear regression. So, let's go really quick back to our just chatting. And okay, so now's the time for questions. Let's see, we'll go to like 9:30, all right? It's 2.5 hours. I stuck with my schedule. And then also I can maybe chop some of this off if Matt and I want to talk dirty secrets about work drama. And so Arrhythmia, you said, when you're talking about multicollinearity, did you discuss detecting it? I'll be rewatching the VOD. Yes. And so we talked about using a correlation matrix to look at linear relationships between different parts of your feature vector. And so you're going to want to use something similar. It doesn't have to be Panda's .core method, but you're going to want to use something similar to detect multicollinearity. Before you leave again, can you show the lasso error equation? Sure thing. Oh God, my handwriting's horrible. Also, this will be in the notes that I will be putting. What the hell is the scene named? There we go. So I believe this is what you need, but I'll be putting these beautifully, typed out in LaTeX in the notes. So have no fear. They won't look this awful when I put them on GitHub. But yeah, are there any other questions before we wrap up for the day? Tomorrow, like I said, we'll be doing logistic regression. 1K, let me know when you're done, and I'll switch back because I have the stream schedule. So I'll show people what's coming up soon when you are done. Copying down Lasso. Okay, you got it. Sweet. All right. So here is our schedule. And that's probably hard to see. But let's see, can I mess with it at all? I'll make it like a little bigger. I don't know. There you go. All right. So today, linear regression. You all have stuck through with that. We can check that off our list. Tomorrow, we'll be doing logistic regression. And thank you for following SunZoj. And then Monday, we'll be doing classification. Tuesday, I'm actually going to be Skyping into some physics classrooms to do a presentation, so can't do anything Tuesday. But Wednesday, we'll do some ensembling. Then there's a little bit of a break for Christmas also because, this is how much I love you all, is like, this is my 2 weeks of PTO for the holidays. So I want to give myself a couple days off where I'm not like panicking in my PJs trying to type out notes to make sure I'm like my code works and stuff. But there's some really cool things ahead. I can't wait for reinforcement learning. That is one of my favorite things about machine learning. So hopefully you all will be here for that. There will be a stream on New Year's Eve, but it probably won't be machine learning. That is this stream's 3-year anniversary. I haven't decided what we're going to do. So if any of you feel like you've got something you're craving, usually we've always done video games and just hung out and gotten a little tipsy and had fun. But that was my first stream was 3 years ago on New Year's. So figure we should do something fun. Thank you for following Pale Blue Zebra. What an excellent name. But yeah, NLP, computer vision, there's going to be some cool stuff. So stay tuned, my friends. Actually, while I have so many of you here, are you ready for the best way that my stream ends? You can't all run away, though. Seriously. Sometimes when I do the be right back screen, like people just flee. The way that I like to end my streams is with my dog singing, because he sings to Star Trek and Stargate. And so I usually like to do a stream poll. Let's see. Lophone, can you do like a straw poll since the stream poll is not ready? Oh no, but get ready. Our stream polls haven't been working for a bit, thanks Twitch. But if you can do a straw poll, so we can have people vote. My dog Tennessee loves to serenade you all, mostly because he gets cheese, but also because he's a very good boy. And that is the best way to wrap the stream up. So, hi Matt the Fisher, welcome. Or Ma the Fisher, excuse me. But if you will stick around briefly, let me put away my green screen so that you all can see my dog. And then we'll come back and he will serenade you with his beautiful voice. It is the most hysterical thing. I actually think we have a little command here if you'd like to get a preview. Nope, is it Tennessee? There you go. You can see him singing to Deep Space Nine there, back when I had hair. But otherwise, please don't go away. I'm going to go get him. Lophone will put a poll in the chat. So vote for what you want him to sing. And we're going to wrap stream up with some dog singing, which is the best way. All right, I'll be right back. All right, friends. Actually, I don't think I need these now. Okay. So we have the bribe. We have some cheese. I know you're a good boy. Let's make this big so everyone can see you. Hold on. Give me 1 sec to remove the weird filters from my webcam. For the green screen. Remove that. We'll remove that. Oh, I know. Everybody wants to see you because you're a good boy. I know. And then we'll close the schedule. Thank you so much, 0% of salt, for following. Those of you who are just tuning in, I know, Tenn, you're such a good boy. It's okay, Tenn. We are doing the 12 days of machine learning miss. You can see up there. stop by tomorrow for logistic regression. But in the meantime, clearly, we need to hear from the stream diva. All right, Tenn. Okay. So it looks like, let's refresh. And some of you who don't like dogs left. How dare you? Okay, next generation. You guys got it. All right, Tenn. You ready to sing? You ready to sing? You're sneezing because you're excited. Oh, hello. Okay. Star Trek TNG theme. Oh, my YouTube searches are just Star Trek. All right. I know, you're a good boy. What's this? Oh my gosh, what's this? Is this the cheese you want? All right. So, volume warning, I'm going to turn it down because he shrieks a little bit. But here you go. Loafbone, find us someone to raid. I know, baby. Hold on, I'm turning it up. Good boy. Good boy. I know, Tenn, you're a good boy. Is he lying or trying to remember? I forgot my body language. He's trying to remember because I swear he actually knows the songs. Like, sometimes he jumps the gun, he gets too excited, so he'll start the next part of the song early. But when he's on, like, he has parts he really likes, so he starts really shrieking. You're a good boy, Tenn. But no, he really does know the songs. All right, so we are going to raid this wonderful person who is doing a charity stream. So please try to stick around as always. Let's try to give some love. And let's tell them all about machine learning, all right? Let's go. And I'll see you all tomorrow. Have a good night.